Welcome to part 3 of how to answer the energy booklet calculations. Make sure you've watched part 1 and part 2 and of course downloaded the booklet and had a go at these questions first. The link for that download is down below. So this first question here we're going to start with today is question 14, and this tells us that we're going to calculate the power output. So power is our output there, and we get given 120,000 joules of work and 8 seconds. So using all of those, we should recognise that the calculation we want to use for this question is power equals energy divided by time. Now we want to work out the power. It's worth 2 marks. There's probably not a rearrangement involved in this. The energy transferred or the work done is 120,000. We divide that by the time. There's no conversion there. It's already in 8 seconds. So 120,000 divided by 8, that will give us 90. It won't give us 15,000. Okay, and there's our answer. Next, the lift goes up 14 meters. That's going to be key. The total mass of the people in the lift is 280. So already at this point here, we should be guessing what calculation we're going to be using. And we get given the gravitational field strength of 9.8. And we want to calculate the increase in GPE of the people in the lift. And then our answer to 2 significant figures. And the fact here we've got 3 marks here suggests we have to do that conversion to significant figures. So gravitational potential energy is mass times g times height. And we're given our mass of 280. G, gravitational field strength, it wants us to use 9.8 newtons per kilogram. And the height here goes up 14 meters. Now, when we plug that into our calculator, that should equal 38,416. Now, we want our answer to 2 significant figures. So that there would give you 2 marks. And the third mark will be from knocking it down, rounding it down to 2 sig figs to 38,000. Question 15. An electric kettle is being used. Now we want to calculate the energy transferred to the surroundings from the water. Now there's a clue here for which calculation to use because it says the heat capacity of water. It tells us the mass of the water and it tells us the temperature difference here. So this calculation, if you recall, for the specific heat capacity is that change in thermal energy equals the mass times the heat capacity times the change in temperature. Now we're going to calculate the energy transferred, so we don't have to rearrange it. Again, there's a clue here, it's only 2 marks. So the mass is 0.5 times the heat capacity, 4,200, times the change in temperature, and it's already worked that out for us, it's 22, which will give us an answer of 46,200 joules. Next up, it says, during one morning, a total of 4,070,000 joules of energy is transferred from the electric immersion heater. 4,030,000 joules of energy are transferred to the water. Calculate the proportion of the total energy transferred to the water. Now at first this might seem a little bit challenging because of some of the wording there, but notice, look, it's only worth 2 marks. So what it really wants is an efficiency calculation. Remember, efficiency in the back of your mind should be it's the useful energy divided by the total energy. So our useful energy here is, remember, that is always going to be less than the total energy. Okay, so we've used these 2 numbers and then we plug it in to our calculator And then we can even times that by 100 itself. And then we get 99%. So the proportion of total energy transferred to the water is 99% of that water. The power output of the immersion heater is 5,000 watts. That's going to be key. Calculate the time taken for the immersion heater to transfer 4,070,000 joules of that energy. Give the unit. So we want the time taken. So we want the time taken here. The unit for time taken should become obvious. We should know that's seconds. So that's going to be a mole. That time taken should be in seconds. Now we get given 5,000 watts. That's the power. So again, the calculation we want to be looking at is power equals energy transferred divided by time. Now, we don't know what time is, but let's put our numbers in and what we do know. So we'll just substitute the symbols here for the numbers. So the power is going to be 5,000. That is equal to the energy transferred divided by the time taken. So we then want to rearrange this calculation as follows. So 4,070,000 divided by 5,000 gives an answer of 815. So going through these marking points here, it will be the unit in seconds, get our answer. We've got our rearrangement and we've substituted our numbers. It's really important we do all of those steps to get all of the marks. Question 17 here. It says a light bulb was a power input of 40 watts and a mains potential difference of 230 volts. Calculate the current of the light bulb. So for this one here, it's handy to know that power equals current times voltage. And we want the current there, but let's substitute the numbers that we have. So power is going to be 40, and that's equal to the current, which we're not quite sure of, but times our voltage of 230. So we've now substituted our numbers, and we can now rearrange that. 40 divided by 230, and that will give us an answer of 0.17 amps. So again, just to clarify where the marks are coming from, answer, rearrangement, substitution. We've got a table here, 3 different light bulbs. Calculate the value of X. So we've got this calculation here, efficiency equals useful divided by our total. Now it tells us our efficiency here as 0.3, and we want to work out our useful. We're not quite sure of that, but we've got our total. Our total is 9. We then want to rearrange that calculation just like we would do normally, of 0.3 times 9 with an answer of 2.7 watts. Next up, we've got a question with lots of standard forming. Don't let this confuse you. Remember, just get those numbers down of what the calculation you want to do. So during 1 year, 1.25 times 10 to the power of 18 joules of energy was transferred from the national grid. This is the number of seconds in 1 year is 3.16 times 10 to the power of 7. So these are big numbers. And we want to calculate the mean energy transferred from the national grid each second. So for this one here, the calculation we want to do is 1.25 times 10 to the power of 18 divided by the time in seconds, because we want to work it out really per second, which gives an answer of 3.06 times 10 to the power of 10 Well done if you got that one right. But as I say, don't let standard form scare you. This is one of the reasons why it's important to have your own calculator, so you can play around with standard form and you know where those buttons are. Question here on solar power. It says the charge flow through the cable between the solar cells and the battery in 24 hours was 27,000 coulombs, and we want to calculate the mean current. So when we look at this one here, we want to look at the calculation that charge equals current times time. What's important about time, however, is that is in 24 hours, but we want the time in seconds. So the time in seconds, we want to work it out. 24 times 60 times 60, that's 86,400 seconds, and that's going to be important. It's got 4 marks here. That's going to be a mark for that conversion. So then we can substitute our numbers. So the charge is going to be 27,000. Now, we don't know what the current is, so we want to work that out, times the time in seconds. So once again, there's 86,400 seconds in 24 hours. We can then rearrange this. 27,000 divided by 86,400, and that will give us a mean current of 0.3125 amps. And at one time, the total power was 7.8 kilowatts with the efficiency of 0.15. Now, notice we've got kilowatts here, so you might be thinking now, okay, well, let's change that to watts. That's going to be a conversion. And there's also a clue there. It's more than 2 marks. There's going to be something to do. We've got 7,800 watts. That's already a mark. And just like before with the efficiency calculations, we've got to do a bit of rearrangement. So the efficiency it's telling us is 0.15. We want to work out the useful power, and we get given the total. So we have to rearrange that by timesing them together. That will give us an answer of 1,170 watts. Next question is one that confuses many pupils. So let's have a look at the information it gives us. It gives us an ice cube with a temperature of minus 15 degrees Celsius. The total thermal energy needed to raise the temperature of the ice cube to 0 degrees Celsius and completely melt the ice is 5,848 joules. Now it gives us 2 bits of information here, which suggests that we've got to do 2 calculations. It's a multi-step calculation, and the fact we've got 5 marks here suggests that. So we've got heat capacity and we've got latent heat. So for heat capacity, the energy, remember, equals the mass times the heat capacity times the change in temperature. So what do we have here? Now the energy is 5,848, but that is for both the latent heat and the heat capacity. Remember, the latent heat is used when we have a change of state. The heat capacity is the heating of 1 kilogram of a material by 1 degree Celsius. So when we put our numbers in here, we want to work out our mass, but we get given the heat capacity. That's nice. And the temperature change has gone from minus 15 to 0 degrees Celsius. So in total, the change in temperature is 15 degrees. We can also look at the latent heat calculation. So the energy here is the mass times the latent heat. But again, we don't know what the mass is. But we do know the latent heat is 334,000. So we've got to add these two together, right? And that will then give us a clue to the energy and the mass. So for the first one here, we've got 2,100 times 15, which should give us an answer when we plug it into the calculator of 31,500. And we've just got the 334,000 here for the latent heat calculation. So we've fine-tuned this one a little bit more. So the energy in total that we have, we know is going to be 5,848. And that is going to be equal to the mass. And then we've got 31,500 plus 3,000. So 334,000. We then need to rearrange this calculation. 5,848 divided by our two answers, which when we do that will give us a nice answer of 0.016 kilograms. So we're going to get marks for substituting our latent heat and heat capacity calculations. We're going to get marks for the adding them together. We're going to get marks for rearrangement. Then we're going to get a mark for our answer. Question 20. When a ramp horizontal, the moment caused by the weight of the ramp is 924 Newton meters. The spring is stretched by 0.25 meters. Calculate the elastic potential energy stored in the stretched spring. So the elastic potential energy, remember, is going to be half times the spring constant times the extension squared. So let's put our numbers in here. We've got 0.5 times our spring constant. Now, our spring constant, we haven't actually got at the minute. And we have got, though, however, the extension. And the extension is going to be 0.2 squared. So we've then got to do another calculation. And what do we have here? We've got a moment. So that's got to be used somewhere. We've also got here the distance from the pivot. So we have a distance given in the calculation there as well. So we want to use another calculation. This is remember it's a multi-step calculation. We know that a moment is equal to its force times distance. So the moment here is 924 Newton meters, and that is equal to the force times the total distance, which is 0.15. And then when we rearrange that, we have 6,160. So we've got now a force. We can then use the calculation we knew when we did probably about Hooke's law, is that the force is equal to the spring constant times the extension. So the force here is 6,160 newtons is equal to the K, the spring constant, which we're not quite sure on yet, times the extension, and the extension we know is 0.250. So we can rearrange that calculation. So there's lots of rearrangement here, but this is worth 6 marks. 6,160 divided by 0.250, and that will give us a K, right, that spring constant, of 24,640. So we can then plug that in here. We've got 24,640, and then we'll get a nice answer when we times this calculation all together of 770 joules. Well done if you have got 6 marks on that. Look, there are 3 separate calculations you've got to be aware of. Definitely a higher tier question. Really pushing for grade 9 if you got that one correct. Question 21, and I love these calculations. All right, is really looking at the relationship between GPE and kinetic energy. So gravitational potential energy, remember, is equal to the kinetic energy. And that's going to be key to remember the context behind everything that we have here. So we want to calculate the maximum possible speed when it reaches position B. And here's position B. So it's going from A and it's going down position B. So it's starting up high. So because it's starting up high, we know we've got to look at gravitational potential energy. Remember, that's mass times gravitational field strength times height. The mass of the toy car is 0.04 times g, which tells us it's 9.8 here, times the height. And it tells us the height, oh, here it is, at 90 centimetres. So that, you have to translate to metres, it's going to be 0.9 metres at 0.9. When we times all this together, we'll get an answer of 0.3528. Right, so that's going to be joules. We can then work out our kinetic energy. Our kinetic energy is equal to half times mass times velocity squared. So what do we know? Well, we know that half is 0.5. Actually, 2 seconds, let's go back. We know, sorry, I should say that our total energy for this calculation here is going to be the same as our GPE because it's equal. So our total energy in this conserved system, 3528, is equal to 0.5 times the mass of the car. And the mass of the car is 0.04 times the velocity squared. And this is what we've got to try and work out. So to work out velocity squared, it's going to be, when we do it for our calculation, it's kinetic energy divided by half times mass for that rearrangement. But we don't want that, we want velocity. So the opposite of a square is a square root. So we want the square root of the kinetic energy divided by the half times the mass. So we plug our numbers in here. Our kinetic energy is 0.3528 divided by 0.5 times 0.04. And then, once we plug that into our calculator with a square root, we should get an answer. Once we get our answer, the square root will be the square root of 17.64, which will give us an answer of 4.2 meters per second. So this car here was travelling at 4.2 meters per second. 5 marks available. So these last 2 questions here are worth a lot of marks. So it's well worth looking at your multi-step calculations. I'll do another video later on with some more examples of these. Anyway, I hope these 3 videos helped you answer and explains some of these calculations from the booklet. These are all past paper questions, so it's well worth practicing. Why not print another copy off and have a go in a few weeks' time, and hopefully you'll see some of your marks improved. If this has helped you, please leave a comment. If you want me to go through any of these other calculations with some more examples, again leave a comment which calculation